Welcome. We are now ready to look at hypothesis testing of two populations in the case of matched pairs or dependent data. So in order to explain, give you a feel for it, let me just read our first example. So it says a study was conducted to investigate how effective a new diet was in lowering cholesterol. So they took a random sample of subjects that participated in the study, and they recorded that subject's cholesterol level before starting this diet, and then took their cholesterol after starting this diet. And what we're interested in is whether we can show that we have good evidence that if anybody followed this diet, that it would be effective in reducing cholesterol. So as always, we're going to use a set of sample subjects to try to draw a conclusion about a population. All right, so at the top here, when we're working with dependent samples, again called matched pairs, what we'll be looking at is the difference between those matched pair values. So we'll be interested in the difference. So we're going to do capital D there, the difference in their cholesterol level before minus after. Now, we can do those differences by hand, of course. So I could take this subject A's cholesterol level before and subtract the cholesterol level after going on this diet. And I'm seeing a difference in cholesterol of 10. Okay, I could do that for every subject, but I'm going to show you on the calculator how we can have the calculator calculate the differences for us. So what I'm going to do is I'm going to enter every subject's before data in L1, my first list, and I'll enter their after data in my second list. So if you wanted to pause and put that data in, I've already loaded mine here. So L1 before and L2 is their after cholesterol level. Okay. So once you have the data in, I'm going to show you how to find the differences and put those results in L3. So essentially, what I'm going to put in L3 is the difference between the L1 and the L2 values. All right, so on my calculator, I'm going to highlight L3. And then I'm going to type L1. So above your 1 is your L1. So second 1, we'll put your L1 on the screen, and then minus. And then above 2 is L2. So second 2, we'll do the L2. And again, as long as you've highlighted up top L3, when I hit enter, it'll populate that column with the differences. So there I see the first difference, and now I can fill in the rest. So the next one was a difference of 3, and then 16, negative 11. I'm going to stop there for a moment. Negative 11. What happened there? So subject D, their cholesterol was 198 before the diet, and then it actually went up. So when I subtract those two values, 209 is larger than 198, and that's why we're getting that result as a negative. All right, then we go on to subject E here. So let's fill in the rest. So that one is negative 1, 15, 27, 17, and 21. Okay. So let me talk about our differences then and the resulting sign, positive or negative, on those values. So if we're letting D, the difference between the before cholesterol and the after cholesterol, what we'll be doing is doing a hypothesis test on the population mean difference between those numbers. So we're going to base this on a sample. So let's just take a look at those values. So for those values, if we average those numbers, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9 subjects. If I average those numbers, that would be X bar because it's a sample, and then it'd be the mean, the sample mean of those differences. So I'm just going to record that value now by using 1-bar stats. So let me do stat calculate 1-bar stats. Now, the thing I want to find the statistics for, it's the data in L3. So I do have to tell the calculator to look at list 3. So above the 3 is your L3. So I'll say second L3. And that value at the top then is the average of those 10 numbers. And I'm just recording this for information purposes. I'll round that to 1 decimal place. So that's 10.8. So on average, I'm getting a value that is positive for the sample. And we're going to be using that information to test a claim about the difference for the entire population. All right, so let's talk about cholesterol levels. So if the claim is true, we're testing the claim that their cholesterol will go down after being on the diet. Then in terms of mu D, the mean difference, what we're after here is, do we expect that number to be a positive number, a negative number, or maybe just something other than 0? So in this case, coming up here, if it is true that the diet lowers cholesterol, then what I would expect to happen generally is the before diet cholesterol level would be the higher number. And I'd be subtracting, so that would be a higher number. And I'd be subtracting the after cholesterol level. So if the diet does work, if the diet does work, I would expect that to be a lower number. So like this scenario, high number minus low number. So I would expect that difference to be a positive number. So not necessarily for each person, but on average, are we seeing the average of those numbers turning out to be positive? So if cholesterol is lower after their diet, then I would expect the difference between the numbers to be positive. So what's very different about this section is that rather than just converting the comparison word, this one says are lower, we have to think a little bit harder about what the difference between the values will be in terms of positive, negative, or possibly just something other than 0. All right, so we're doing all that because to write the claim takes a little more effort here. So the mean, population mean difference, if cholesterol levels work, that difference will be a positive number. And positive numbers are numbers that are greater than 0. So that's what positive means. We're just going to write it in English over here, greater than 0. So we've got a little bit of thought process there to get our claim. And then the null hypothesis, as always, is the same symbol, but now we have an equal, and that one will be equal to 0. So when we enter this on our calculator, this will be our mu naught. So we'll have mu naught equals 0. All right, and let's go ahead and run our test. So when we're dealing with matched pairs, it's going to come up to the top here. We're going to be running a t-test on the differences between the data values, so between these matched pairs. Okay, so now we've got our differences in L3. So let's go to our tests. So stat tests. We're going to run a t-test, a regular t-test on the data that's in L3. My mu naught is 0, so you want 0 there. And then for the list, you want to make sure that says L3. So it most likely says L1 if we haven't done a problem like this yet. So you want to switch yourself to L3. Frequency always stays 1. That just means one of each number is present in that list. And then for the direction of your test, you want to do a right tail test, so a greater. And then we'll go calculate. And we're only going to do p-value method for the matched pairs. So I do see my test value there, but let's go right to the heart of it and write down our p-value. So 0.0130. And again, I like to write it as a percent. So that'd be 1.30%. And then we ask ourselves, is the p-value low? If so, we let the null go. So we have to compare our p-value to our alpha, our significance level. I did not write that down yet, but at the top it said to use alpha 5%. So if I compare that to 5% alpha, 1.3% is indeed less than 5%. And technically we say less than or equal to, but you can just say less is fine. So my p-value is low. P-value less than alpha, p-value low, decision let the null go. Let's add a little nicer. And when you reject the null, you support your claim. So it appears that we do have evidence based on this group of 9 subjects. We do have enough evidence to support a claim that the diet reduces subjects' cholesterol levels. All right, and that is how we handle matched pairs.